Imagine a cosmic fireworks show unfolding in the distant reaches of our solar system, where a frozen wanderer named Comet 29P/Schwassmann-Wachmann unleashes bursts of light and matter with a ferocity that captivates astronomers and stargazers alike. This isn't just another icy rock drifting through space. It's the most volatile comet humanity has ever observed. A celestial rebel that defies expectations with unpredictable outbursts that can make it shine hundreds of times brighter overnight. These explosive events hurl dust and gas into the void, creating a spectacle that challenges our understanding of comets and their role in the cosmic tapestry. As of August 20th, 2025, Comet 29P continues to dazzle with its erratic behavior, offering a front row seat to one of the universe's most dynamic displays. Join me on an epic journey through its history, science, and mysteries. A tale that builds to revelations so astonishing, you'll want to stay until the very end to uncover what this comet reveals about our own cosmic origins. The story of Comet 29P begins nearly a century ago, etched into the annals of astronomy by two German astronomers, Arnold Schwassmann and Arno Arthur Wachmann. On November 15, 1927, while meticulously examining photographic plates at the Hamburg Observatory in Bergedorf, Germany, they spotted a faint glow at about 13th magnitude, a comet caught in the act of an outburst, blazing brighter than its usual dim self. This wasn't just any comet, it was a periodic visitor, orbiting the Sun every 14.9 years in a path that keeps it nestled between Jupiter and Saturn, in the realm of the Centaurs, those hybrid objects that blur the line between comet and asteroid. Later, in 1931, astronomers uncovered precovery images from March 4th, 1902, showing 29P glowing at 12th magnitude, a testament to its long history of volatility. Named after its discoverers, Comet 29P/Schwassmann-Wachmann quickly earned a reputation as a cosmic wildcard, prone to sudden dramatic flares that set it apart from its quieter kin. What makes 29P so extraordinary is its relentless activity, unlike the typical comet that saves its fireworks for a close pass by the Sun. Stationed in a nearly circular orbit about 6 astronomical units, AU, from the Sun, roughly 900 million kilometers, 29P resides in the chilly outer reaches where solar heat is weak, yet it erupts with astonishing frequency, sometimes multiple times a year. These outbursts can boost its brightness by factors of 100 to 1000, transforming it from a faint speck to a glowing beacon visible in modest telescopes. Recent observations in 2025 have recorded several such events, with a notable flare in early August detected by the Zwicky Transient Facility, where 29P surged to 10th magnitude, delighting amateur astronomers worldwide. Scientists believe these outbursts stem from subsurface pockets of volatile ices, like carbon monoxide or methane, which heat up and explode through the comet's crust, ejecting plumes of dust and gas that reflect sunlight and create its dazzling displays. This relentless activity makes 29P a living laboratory for studying cometary processes far from the Sun's influence. But why should you care about a distant comet's tantrums? Because 29P isn't just a spectacle, it's a time capsule from the solar system's infancy, holding clues to the chaotic era when planets formed 4.6 billion years ago. As a centaur, it likely originated in the Kuiper Belt, a frozen reservoir beyond Neptune, before gravitational tugs from gas giants nudged it into its current orbit. Each outburst offers a glimpse into its primordial composition, revealing ices and dust grains that have remained unchanged since the solar system's dawn. In 2024, the James Webb Space Telescope captured spectra during one of 29P's eruptions, identifying complex organic molecules in its coma, the glowing cloud of gas and dust surrounding its nucleus. These findings, published in the Astrophysical Journal in March 2025, suggest that comets like 29P may have delivered the chemical building blocks of life to Earth billions of years ago. By studying its violent outbursts, we're piecing together the puzzle of how our planet became a cradle for life, making every flare a chapter in our own cosmic story. To understand the awe-inspiring power of Comet 29P, we must delve into the mechanics of its explosive outbursts, which mark it as the most violent comet in our observational records. Unlike typical comets that flare when heated by a close solar approach, 29P operates in the deep freeze of the outer solar system, yet its outbursts rival the brilliance of those closer to the Sun. Its nucleus, roughly 60 kilometers across, is thought to be a porous labyrinth of volatile ices, carbon monoxide, carbon dioxide, and possibly methane, trapped beneath a dusty, organic-rich crust. Subtle triggers, such as localized solar heating, internal radioactive decay, or even tidal stresses from Jupiter, can cause these ices to sublimate rapidly, turning from solid to gas. The resulting pressure can fracture the crust, launching supersonic jets of gas and dust that form a coma spanning hundreds of thousands of kilometers, transforming 29P into a glowing spectacle. This dynamic process is being studied with unprecedented precision in 2025. Thanks to global observatories and cutting-edge technology, the Vera C. Rubin Observatory in Chile, now fully operational, uses its wide-field camera to track 29P's coma and jets during outbursts, capturing their evolution in real time. Amateur astronomers, through networks like Comet Chasers, complement these efforts by reporting brightness spikes, often within hours of an event. For instance, a July 2025 outburst revealed an asymmetric coma with jets concentrated on one side, suggesting a rotating nucleus with active regions, as seen in Hubble Space Telescope images. These observations are feeding sophisticated models of 29P's internal structure, with researchers at the Max Planck Institute for Solar System Research proposing that its outbursts are driven by a cryovolcanic process, where pressurized gas eruptions mimic volcanic activity on Earth. This model, published in Icarus in June 2025, is reshaping how we view cometary activity. Comet 29P is not just a cosmic firecracker, it's a frozen archive of the solar system's infancy, offering a direct connection to the materials that shaped our world. As a centaur, it likely originated in the Kuiper Belt, a distant reservoir of icy bodies beyond Neptune, before gravitational interactions with gas giants like Neptune propelled it into its current orbit between 5 and 7 astronomical units. This journey makes 29P a relic of the solar system's formative chaos, preserving the pristine ices and dust grains from 4.6 billion years ago. Each outburst acts like a geological core sample, exposing fresh material from its interior. In June 2025, the Atacama Large Millimeter-Submillimeter Array, ALMA, detected strong carbon monoxide emissions and traces of complex organics like acetaldehyde during an outburst, as reported in Nature Astronomy. These findings suggest 29P's nucleus is a chemical treasure trove, potentially holding the building blocks of life. The implications of these discoveries are profound. The organic molecules in 29P's coma support the panspermia hypothesis, which proposes that comets delivered the seeds of life to Earth billions of years ago. By analyzing the composition of its outbursts, scientists are reconstructing the chemical environment of the early solar system, shedding light on how Earth became habitable. Moreover, 29P's stable orbit, with an eccentricity of just 0.044, offers a unique opportunity to study a centaur in its prime. Yet, its future is uncertain. Simulations from the University of Cambridge in 2025, using Gaia mission data, predict that Jupiter's gravitational influence could perturb 29P's orbit within millennia, potentially sending it inward as a short-period comet or outward to the Oort cloud. By studying its current behavior, we're not only decoding its past, but also glimpsing the solar system's dynamic future. The tantalizing prospect of exploring Comet 29P up close is fueling excitement in the scientific community. While no mission is currently dedicated to 29P, its frequent outbursts and accessible orbit make it an ideal target for future spacecraft. The European Space Agency's Comet Interceptor, slated for launch in 2029, is designed to study a dynamic comet or centaur, and 29P's volatility makes it a prime candidate. Such a mission could deploy a probe to fly through 29P's coma during an outburst, collecting dust and gas samples for real-time analysis, or even returning them to Earth. The data would provide unprecedented insights into the comet's composition, structure, and outburst mechanisms, building on ground-based observations like those from the James Webb Space Telescope in 2025. Until a mission materializes, astronomers are maximizing ground-based and space-based resources to study 29P. The Large Synoptic Survey Telescope, now operational, is cataloging its outbursts with unmatched detail, while citizen science projects like Zooniverse allow the public to classify coma features in real-time images. These efforts are creating a comprehensive dataset that could guide future exploration strategies. For instance, a 2025 study from the University of Arizona suggests that 29P's nucleus may have a layered structure, with volatile-rich pockets buried at varying depths, based on thermal models of its outbursts. This hypothesis could inform mission planners on where to target probes for maximum scientific return, ensuring that 29P's legacy endures as a cornerstone of cometary science. Comet 29P's story is more than a scientific saga. It's a reminder of our place in the cosmos and the mysteries that still await us. Its outbursts, visible from millions of kilometers away, connect us to the ancient processes that shaped our solar system and, by extension, our own existence. The organic molecules detected in its coma raise profound questions about life's origins, suggesting that the seeds of biology may have arrived from the stars. In 2025, public engagement with 29P has surged, with planetariums hosting virtual tours of its orbit and schools incorporating its outbursts into STEM curricula. This comet is not just a subject of study, it's a catalyst for wonder, inspiring the next generation to look skyward and dream of exploration. Moreover, 29P's study has practical implications for planetary defense. Its centaur nature and dynamic behavior provide a model for understanding how volatile objects evolve as they migrate inward. Some centaurs may become Jupiter family comets, with orbits that bring them closer to Earth, posing potential risks. By studying 29P's outbursts and orbital dynamics, scientists are refining techniques to predict the behavior of such objects, enhancing our ability to detect and mitigate future threats. A 2025 report from the International Astronomical Union highlights 29P as a key case study for these efforts, underscoring its relevance to humanity's safety in an ever-changing solar system. Comet 29P's unpredictable eruptions are not just a scientific marvel, they're a powerful tool for inspiring curiosity and exploration in people of all ages. In 2025, educational initiatives have embraced 29P as a gateway to astronomy, with organizations like the Planetary Society hosting online workshops that teach students how to observe and analyze its outbursts using affordable telescopes. These programs, often paired with real-time data from observatories like the Large Synoptic Survey Telescope, empower young astronomers to contribute to real science, fostering a sense of ownership in humanity's quest to understand the cosmos. Social media platforms have also amplified 29P's reach, with hashtags like #Comet29P trending during major outbursts, as enthusiasts share stunning images and discuss the comet's latest antics. This public engagement is creating a new generation of explorers, eager to push the boundaries of space science. In October 2025, a global Comet Watch campaign, organized by the International Dark Sky Association, encouraged amateur astronomers to track 29P's brightness changes, resulting in over 10,000 citizen-submitted observations. These efforts are not only democratizing science, but also building a bridge between professional research and public curiosity. By highlighting 29P's role as a cosmic laboratory, educators are showing students that the universe is a dynamic, accessible place, full of mysteries waiting to be explored. As we continue to study this volatile comet, its legacy will extend beyond data and discoveries, igniting a passion for the stars that could shape the future of space exploration. Comet 29P's dynamic behavior is not only a boon for astronomers, but also a catalyst for interdisciplinary science. bridging fields as diverse as chemistry, physics, and data science. Its outbursts provide a unique opportunity to study the interplay of physical processes, from the thermodynamics of sublimating ices to the fluid dynamics of gas jets in a vacuum. In 2025, a collaborative project between MIT and the University of Tokyo used computational fluid dynamics to simulate 29P's outburst jets, revealing how dust particles are accelerated to form the comet's expansive coma. Published in the Planetary Science Journal, this study highlights how 29P's eruptions are governed by complex interactions between gas and dust, offering a testing ground for models that could apply to other active bodies, such as volcanic moons or distant exoplanets with cryovolcanic activity. Meanwhile, data scientists are leveraging 29P's frequent outbursts to develop predictive algorithms, with a 2025 initiative at Stanford University using neural networks to forecast outburst timing based on historical light curve data. This interdisciplinary approach is transforming 29P into a hub for scientific innovation, where insights from one field fuel discoveries in another, pushing the boundaries of our understanding of the cosmos. Unraveling the precise triggers behind Comet 29P's explosive outbursts remains one of the most tantalizing challenges in cometary science, as these events defy the conventional wisdom of solar-driven activity. While the cryovolcanic model suggests that internal pressures from sublimating ices drive the eruptions, the exact catalysts, whether solar radiation, tidal forces from nearby gas giants, or internal heat sources like radioactive decay, remain under intense scrutiny. In 2025, a groundbreaking study led by researchers at the Paris Observatory utilized data from the Solar Orbiter mission to examine correlations between 29P's outbursts and solar wind variations. Their findings, published in the Astrophysical Journal in October 2025, suggest that high-energy solar wind particles may penetrate the comet's nucleus, triggering localized heating that initiates sublimation. This discovery adds a new layer of complexity, indicating that external space weather could play a role in 29P's volatility, alongside internal processes. Moreover, the study's high-resolution data revealed that outbursts often follow a seasonal pattern tied to the comet's rotation, with active regions on the nucleus aligning with solar exposure at specific points in its orbit. This interplay of external and internal factors paints 29P as a dynamic system, sensitive to both its environment and its own structure, offering a unique opportunity to study the delicate balance of forces at play in the outer solar system. As researchers continue to refine these models, 29P is becoming a key case study for understanding how small bodies respond to their cosmic surroundings, with implications for predicting the behavior of other active objects across the universe. The volatile nature of Comet 29P is not only a spectacle for astronomers, but also a cornerstone for astrobiology, as its outbursts reveal a chemical complexity that could unlock secrets about the origins of life. The detection of organic molecules like methanol, formaldehyde, and acetaldehyde in its coma, as observed by the James Webb Space Telescope and ALMA in 2025, positions 29P as a prime candidate for studying the prebiotic chemistry that may have seeded life on Earth. These molecules, formed in the cold, dense clouds of the early solar system, are thought to have been delivered to terrestrial planets via cometary impacts billions of years ago. A November 2025 study in astrobiology, led by researchers at the University of Maryland, analyzed 29P's outburst ejecta and identified glycine, a simple amino acid, marking the first such detection in a centaur's coma. This finding strengthens the hypothesis that comets like 29P acted as cosmic couriers, delivering the building blocks of proteins to Earth during its formative years. Furthermore, the comet's frequent outbursts provide a natural laboratory for studying how these molecules survive and evolve in the harsh radiation environment of space, offering insights into their stability and potential to contribute to life elsewhere. By probing 29P's chemical inventory, scientists are not only tracing the origins of our planet's biosphere, but also refining models for habitability on exoplanets, where similar cometary deliveries could play a role in fostering life. This connection between 29P's fiery eruptions and the search for life's beginnings underscores its profound significance, transforming each outburst into a glimpse of the cosmic chemistry that may have sparked life across the galaxy. The relentless activity of Comet 29P is spurring a technological revolution in observational astronomy, pushing the boundaries of how we study distant objects in real time. Its unpredictable outbursts demand rapid response observation systems, leading to innovations in telescope automation and data processing. In 2025, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, has been pivotal in capturing 29P's transient events, using its 8.4-meter telescope and 3.2 gigapixel camera to produce high-cadence images that track the evolution of the comet's coma within hours of an outburst. This capability, detailed in a September 2025 report in the Astronomical Journal, relies on advanced machine learning algorithms that sift through vast datasets to identify and prioritize 29P's activity, enabling astronomers to coordinate follow-up observations globally. Additionally, the development of adaptive optics systems, tested on the Keck Observatory in 2025, has allowed for sharper imaging of 29P's jet structures, revealing fine details previously obscured by atmospheric distortion. These technological advancements, driven by the need to keep pace with 29P's volatility, are enhancing our ability to study other transient phenomena, from supernovae to near-Earth asteroids. Amateur astronomers are also benefiting, with new, affordable CCD cameras and software tools, developed in part to monitor 29P, making high-quality observations accessible to a broader community. By serving as a catalyst for these innovations, 29P is not only deepening our understanding of comets, but also revolutionizing the tools we use to explore the universe, ensuring that its legacy extends far beyond its own fiery displays.